Okay, let's get back to work here. So the case of biology that I mentioned is a really nice case because it shows that children understand something about the causal nature of the biological world, even in a more deep, abstract, conceptual way. And it also shows how they're learning about how the biological world works through their daily experiences of things like the death of goldfish. Now what I'm going to do is talk a little bit about physical causality, about when children start to understand that physical objects can also have causal consequences. And then I'm going to segue to talking a little bit about the role that play and exploration play in how children learn about these things. So to start out with, you could ask, how is it that we could tell whether children understand about how causality works? And about 10 years or so ago, we invented this little machine, the Blicket detector, which is a box that lights up and plays music when you put some things on it and not others. And then we set out to see how it is that children understood how machines like this worked, and if they could learn about those machines from data. So let me give you just one example of an experiment that's like this. In the book, they talk about work that my ex-student Dave Sobel has done that's shown that even 18-month-olds can solve some of these kinds of problems. So here's an example of one experiment by Tamar Kushner and I, where what we did was we showed children blocks that either made contact with the detector or didn't make contact with the detector. And then the blocks sometimes made the detector go and sometimes didn't make the detector go. So what happened was that initially children think that you're more likely to activate the detector if you make contact with it than if you don't. So that's a kind of spatiotemporal principle about causality. And we know that some of those spatiotemporal principles are in place even from a very early period, and that's one of the things they talk about in the book. But then what we did was we gave the children this probabilistic data about whether or not the blocks worked. So the children saw that the red block made the machine go 2 out of 3 times, and the blue block made the blue block, which made contact with the machine, made it go 2 out of 6 times. So their sort of spatiotemporal understanding is different from the evidence that they're getting from probabilities. And remember, these are 3 and 4-year-olds, so they're just starting to add and subtract. Nevertheless, after they'd seen the evidence, they were more likely to pick the red block and hold it up, wave it up over top of the machine than they were to pick the blue block and make contact with the machine. So that means that these 3 and 4-year-olds already understood something about the relationship between a pattern of statistics and causality, the way that a particular statistical pattern could tell you whether or not a causal relation was there, the same way that we do when we're scientists. Now, how do children actually get this kind of information in their everyday life? Well, probably the kinds of things that they hear people talk about have an effect. But one thing that seems to play a really important role in this kind of learning in preschoolers is their spontaneous exploratory play. And there's been a bunch of beautiful work just in the last couple of years, so it's not actually in the textbook or in the Scientist in the Crib, that shows the extent to which children's spontaneous play and exploration is helping them to solve these kinds of causal problems. And let me show you So this is a little boy in Christine Laguerre's lab in Austin, and he's actually, what Christine did was she, let's see. What she did was she actually showed the children one of these box detectors.
This on the box.
And then she showed them that it didn't work.
This makes that light up the box.
And then she asked them to just explain why it was that one of the blocks didn't work.
And it's the other side.
Here.
Uh-oh. Nothing. This one's lighting up, and this one's not. So that means... What's making this light up? I don't know. Oh, no. Oh, it's because this needs to be like this, and this needs to be like that. That's why. Oh, why the boxes are the wrong way.
Okay, this is his suggestion to the experiment.
What should we do now?
Oh, because the light goes only to here, not here. Oh, the bottom of this box has electricity in here, but this doesn't have electricity. It's lighting up. So we need to put 4. So we need to put 4 on this one to make it light up, and 2 on this one to make it light up.
Okay, so aside from being incredibly adorable and cute, what Christine found was that, especially when you gave children anomalous evidence they couldn't understand, and then asked them to explain it, you saw these kinds of patterns of hypothesis testing and exploratory play. So that's part of the reason for having the explanation breaks. It would be even better if you guys had a bunch of little children here that you could actually do experiments on in the break, but we can't really arrange that. Even better if you tried to explain it and then tried to do experiments to figure out what the answer was. But what Christine showed was that being prompted to explain helped the children to understand what was going on, and it led to this kind of exploratory play that actually helped them to get to the right solution about how the blocks work. Laura Schultz, who's also an ex-Berkeley student, who's now at MIT, has done a whole bunch of other studies that also show the way that children's play with things like Blicket detectors can lead to their understanding of causal relationships. So here's what they did in this experiment. They showed the children a box that had 2 levers on it that you could press. And what happened is that sometimes what would happen is, in one condition what would happen is the child and the experimenter would both press the levers at the same time. The experimenter said, okay, we're going to do this at the same time. 1, 2, 3, let's both press. And when they did that, 2 puppets popped out of the top. But sometimes what happened, sometimes in the other condition what happened was the experimenter would push one of the levers and one puppet would come out. And then the child would push the other lever and the other puppet would come out. So the experience of these 2 children is very similar, but the children in the first condition don't really understand how the machine works. It could be that both of them make both of them go, it could be one of them makes one go, it could be that the other one makes the other one go. Whereas the children in the second condition actually do understand how the box works. They know that their lever makes one of the puppets go and the experimenter's lever makes the other puppet go. Is that clear to everybody? Then what they did was they actually gave the children this toy plus another new toy, and then they just said, sit and play, and they walked out of the room and let the children play with the toys. And what they discovered was that the children in the first group, the confounded group, when you couldn't figure out, didn't already know how the toy worked, were much more likely to play with the old toy, and less likely to play with the new toy. Whereas the children who did understand how the machine worked were much more likely to play with the new toy. So the children's play seemed to reflect the fact that if they played with the toy, they could find out more about how it worked. So they really seemed to be motivated to try to play with things that would actually give them the information they needed to figure out how the world worked. And another experiment that that Schultz did with the plate detector shows the same thing. So this time what they did was they, again, had two different conditions. And in one condition, so now the children, instead of just having blocks on the liquid detector, had little puff beads. These are the little beads that stick together. And to begin with, one group of children saw that all of the beads made the machine go. So you put each little bead on individually and all of them made it go. In the other condition, the children saw that some of the beads made it go, but only some of them didn't make it go. And then the children saw exactly the same event. They saw two puff beads stuck together put on top of the detector. And again, the experimenters just left the room and left the children to play. Well, again, if you think about it, the all beads condition, there isn't really a causal problem to solve because you know that all of the beads are going to make the machine go. But in the some beads condition, there is a causal problem to solve because you want to know which ones will actually make it go and which ones won't. And what they discovered was that in the some beads condition, the children were much more likely to pull the two pieces apart than in the all beads condition. And then they did a nice variant of the experiment, which was they actually glued the beads together. So now the children couldn't pull the beads apart. And what they discovered was that in this case, when the children were playing, what they did was they took the two beads and then they would move them around like this. So one bead was contacting the detector, and then they moved around the other way, so the other bead was contacting the detector. So in their, they did that in the some condition, but not in the all condition. So the children are actually being very ingenious in their spontaneous play in figuring out how to, just what to do to figure out how the machine worked. So when the children were playing, they were really being like scientists doing little experiments to try to figure out the causal structure. And finally, you might ask, how does this kind of spontaneous play interact with the kind of explicit instruction that you get, say, in a classroom or in school? And here's the experiment. This is Liz Bonowitz, who's now a postdoc in our lab. And what they did was actually show the children this toy that could do different things. So there's a little thing there that squeaks when you push it. There's a light at the end of one of the tubes. There's something else that makes music, and there's a mirror at the tube. And then what they did was they just, again, gave the children this toy and saw what they did. But they had two different conditions. In one condition, the experimenter came in and acted as if she just accidentally figured out one of the things that the toy could do. So here's this.
Hey, Scarlett. My name is Jamie. Hi. The museum gave me this really weird toy. It's so weird. I've never seen this before. Oh, oops. Did you hear that? Did you see that? Weird. I've never seen that before. That is so weird. This is a really cool toy, Scarlett. I want you to play with it and see if you can figure out how it works, okay? Can you let me know when you're done playing? Okay, great. Keep playing, okay?
Okay, so she's just still doing that, right? Now here's the other condition. Now what happens is it's exactly the same sequence of events, except now you'll hear the experimenter is going to say something different.
Hi. I'm going to show you my toy. This is my toy. Isn't it cool?
Yeah. And this is all the thing.
Okay, I'm going to show you how my toy works, Isaac. Watch this. Can you hear that? Can you let me know when you're done? Okay, great.
Okay, so you can see that what happened, again, this isn't just these two children, this was what the experimenters found in general, was that when the children were just spontaneously playing with the toy, they discovered all the different things that the toy could do. So even though the two conditions were almost exactly the same, both of them, remember, they saw the experimenter and the experimenter made it squeak, the way that the children played was really different. In the second condition, where the experimenter said, look, I'm going to show you how this works, and actually gave them explicit instruction, the children did the thing that she did, they pushed the squeaker, but they never actually got around to exploring all the other possible things that the machine could do. So the idea here is that actually being directly instructed rather than having an opportunity to play is kind of a double-edged sword, and in fact they call this article the double-edged sword of pedagogy. Now in some ways, of course, it's an advantage, because if it were true that the only way that the machine worked was to squeak, and the teacher wanted to explain to you that the only way the machine worked was to squeak, then it would be sensible to just zoom in on the squeaking and ignore everything else. But it also means that that can limit the amount of general exploration that children are doing, which might give them the opportunity to discover something new that they didn't actually know already, the way that little boy did when he was playing with the liquid detectors. So this new set of work kind of confirms something that I think people have suspected for quite a while, which is that when children are just spontaneously doing this kind of spontaneous exploratory play, what they're really doing is getting a bunch of information, which then helps them to solve these kinds of physical causal problems. So what we've seen is that in the case of biology, just in their natural spontaneous understanding, children do understand the causal nature of what's going on around them. And data, like seeing a goldfish, is something that can actually help them to learn that. And then in the second part of the lecture, we saw that in terms of their understanding of physical causation, again, they seem to understand really sophisticated things about physical causation from the time they're quite young. But again, their experience, and particularly their experience of their spontaneous play and exploration, seems to play a really big role in enabling us to understand even more about physical causation. And we'll talk about pretend play and the understanding of the mind next time.